Hello guys. In this lecture we continue our journey about Turing machine. Let's see what we got for this lecture. We have learned Turing machines in detail so far, and also we added a cool option, we call it stay option, just for more flexibility. But we know that this stay option does not add any power to the Turing machines. I mean, standard Turing machines and the Turing machines that has a stay option are equivalent. Okay. Now we want to introduce another mode for Turing machine to run. And also we will talk about other models of Turing machines. So far, we use Turing machines for accepting or rejecting strings, but Turing machines can be used as transducers. So first, we need to know what the transducer is. So in physics, transducer is a device that it can convert variation in one kind of physical quantity into electrical signal or vice versa. What variation we are talking about? Variations like movement, pressure, brightness, or so forth. For this course, let me summarize what's the meaning of a transducer. Transducer is a device that converts an input to an output. So just consider it as a black box that we put input and we get some output. Let me take a couple of real world examples from the transducer. For example, microphone is a transducer. Its job is to convert the sound waves here to electrical signals here, right? So this is a transducer, is a physical transducer. Another example is electric generator. So when you move a magnet in front of a coil, it produces electrical power. And this simple picture is showing the principle of how we can generate power. So this is another example of transducer. The next question is, how can we mathematically model a transducer? So just remember an input to an output, right? Yeah, by functions. Yeah, just remember that what was function. Function we define like this. It maps a member of domain to a member of range based on a rule. Just translate this mapping to converting and member of domain to input and member of range to output. Then a function converts an input to an output, which is the definition of a transducer. So we can model mathematically a transducer by a function. So what does it mean? I mean, what do we want to get from this? If this is the case, and if the Turing machines can act like transducers, it means that Turing machines can implement functions. And that's a huge capability for Turing machines that they can implement functions. Okay. Now the question is, if this is the case, then what would be the input and what would be the output of Turing machines? That's a very good question. So the input is whatever we put on the tape. All of the content of the tapes can be considered as the input. What about the output? All or part of the tape's content when machines halt. This is a very important point. The machine should halt. So whatever we get at the end on the tape, all of them or part of them can be considered as output. Bottom line is It is designer responsibility to define the output. Okay? We will be using how the JFlap shows the output. Please note that this lecture is accompanied with a tutorial for JFlap that shows how JFlap considers the output. Actually, that's part of this lecture. Okay, so just watch that and get an idea that how JFlap shows an output. So what is Turing computable function? So far we learned that Turing machine can simulate or implement functions. But do they have a specific name? Yes, we call them Turing computable or just computable. So a function is said to be Turing computable if there exists a Turing machine that implements it. And it has been proved by computer scientists that most mathematical functions are Turing computable. It means that we can implement them with Turing machines. Just note that we just defined the concept of computability. What does it mean? It means that a problem is called computable if there exists a Turing machine for accepting that. And just remember that all problems can be encoded to formal languages. And when we say Turing machine accept it, it means that Turing machine solved that problem. So a problem is called computable if there exists a Turing machine that solve it, right? And this is the meaning of computability. In this section, we're going to talk about how to combine simple Turing machines to solve more complex ones. Okay, so let me explain it through a simple example. Let's say we have two unary numbers. Let's call them x and y, and they are separated with a zero. Okay, so can we separate them with blank? No, it is not the case because we are not allowed to input a string that contains blank, right? So if this is the case, I need to be able to put this combination on the tape, but it has blank. So that's why we use other symbols like zero or any other symbols. Okay, so what is the goal? The goal is we want to design a Turing machine to compute this function. This function has two input, x and y, and if x is greater than y, then we need to have the addition of the x and y, and if x is less than y, we need to clean up everything and just show the zero. Let me visualize what we are looking for. Let's say that x is greater than y. So this is just an example. 111 is greater than 11, of course, right? Then what do we expect to see? We expect to see an addition like this, okay? And just pay attention that where the cursor is pointing at. It's not enough that we just add two ones. We need to move the cursor to the right place. So as we explained, the output will start from where the cursor is pointing to the right until the first blank. So all of these will be output of the JFlap. Let me take an example that when x is less than y, so x is 3, y is 4, and what do we expect to see? Based on this function, we expect to see 0. What does it mean? It means that I need to see a 0 here and cursor that pointing to that, right? And after that, we need to have a blank. Why? Because we want to JFlap shows the 0. In this way, it shows the 0. Something that here you need to pay attention is these question marks. I put question mark here to show you that really we don't care what the content of the rest of the tape is. The only thing that we care is that when the machine stops, we see 0. Okay, so that's a very important point here. Okay, so to implement this function, we would need three parts: a comparer, an adder, and an eraser. So the comparer, an adder, and an eraser. And here is how we combine them. So we put the comparer here. So this is a simple Turing machine whose job is to compare x and y. And if x is greater than or equal to y, then it goes that way. And if x is less than y, it goes this way, right? And these guys are simple Turing machines whose job is, yeah, the adder's job is to just add and move the cursor to the right place. And the eraser's job is just, move the cursor to a 0 and show the right output. You see, this is a very simple example that how can we break down a complex problem to a smaller and simpler problem, and then we combine them to create a more complex Turing machine that solve the entire problem. Okay, so the implementation of this example is so simple. You may implement it as an exercise. Other models of Turing machines? Yeah, let's see what they are. Okay, we witnessed so far that adding memory could increase the computing power a lot. In PDAs, we added a stack, and we noticed that how powerful was that stack with respect to the DFAs. Then we added read-write memory to Turing machines, and we noticed that how much power this read-write memory added to the machine. Now the question is, to make more powerful machines, can we add more memory or other kinds of memories? For example, if I add two or more stacks, or let's say a queue and a stack, or more read-write tapes, can I get more powerful machines? This is a very important question. And how far we can go? What is the ultimate power? So these are the objective of this section. We want to add some extra capabilities to the standard Turing machine and create a new class, of course. And then after that, we would ask this question: is this new class more powerful than the standard Turing machines? So this is the goal of this section. And how can we respond to these questions? We have already seen how we can compare the classes of automata by simulation. And we noticed two types of the simulation. One simulation was just converting the mathematical definitions. Another simulation was the real simulation that we used for comparing PDAs and Turing machines. All right, with this introduction, let's get started. Turing machines with multidimensional-tape. How cool is that? We extend the input-output tape to multidimensional. It means that from everywhere, all sides, it is unbounded. And do we have a cursor? Yeah, this is the cursor. It's a read-write cursor, but it can go left and right and also up and down. So that's why we need to have two coordinates for them. One is showing that from X side. So for example, 3, positive 3, it means positive 3 here, 1, 2, 3 here. And minus 2 is going this way, 1, 2. So we are pointing to this point. What is the difference for formal definition? Yeah, in the formal definition, we still have the septuple, but for the delta function, we just need to add u and d for up and down for the movement symbols. We have a theorem that is saying Turing machines with multidimensional tape is equivalent to a standard Turing machines. So it means that even by changing this tape like this, it does not add any power to a standard Turing machine because we can simulate this kind of Turing machines with just one simple tape. Okay, so in fact, we need to prove two things: multi-dimensional tape simulate standard Turing machines, and the other way around, standard Turing machines simulate multi-tape Turing machines. So for the first one, can multi-dimensional tape simulate a standard Turing machine? Of course it can. It's just a trivial proof because we have several tapes like this, right? We just need to use one of them. If we use just one of them and we don't use that up and down, then it is equivalent to a simple standard Turing machine. So for this one, we have no problem for proof, but for the other way around, I mean simulating the multi-dimensional tape with a standard Turing machine is a big deal. Okay, how can we do that? Yeah, we need to separate the tape. So let's say, for example, here we have the input string, whatever it is, right? We need to simulate, I mean, let's say this is a tape 1, this is a tape 2, and this is a tape 3, and so forth, right? Probably this way the negative part. So if this was the X and Y, and these are the tapes, right? Yeah, this is the tape 1, tape 2, and this is tape minus 1, tape minus 2, and so forth, right? So we need to simulate them on the single tape. It is doable, but of course it's very hard, right? So it means that we can simulate multi-dimensional tape Turing machine with a standard Turing machine. What is the result of this theorem? Yeah, multi-dimensional tape did not add any power to the machines. Multi-tape Turing machines. Let's see what they are. So here is the building blocks of multi-tape Turing machines, the control unit, and let's say this is tape 1. As an example, I am going to show you a double tape, but the idea is extensible to many tapes. This is the tape 1, and this is the tape 2, and each one has independent cursor. Okay, so this is the point. All of the tapes have independent cursors. Okay, let's see how a subrule looks like. So let's say this is a transition for a double tape. So for the double tape, as you see, we need two labels like this that are separated with a vertical bar. If we have more, then we put another vertical bar and put the label here. For the condition for transition, both of the input should be satisfied. In that case, a machine goes from Q2 to Q5 and does this stuff. And here is how the subrule looks like. So if the input is A for the tape number 1, input is E for the tape number 2, then go to Q5 and replace the A to X, E to Y. On tape 1, go to the right, tape 2, go to the left. Yeah, you see, at the beginning it looks like very complex, but it is so easy to use it. Let me visualize this subrule and show you how it works. So as you see, tape 1, it has its own string. Tape 2 has its own string like this. Now let's see what would happen after this transition. The input is A, E, yes, A and E, wherever the cursor is pointing, right? And then change the A to X. Okay, so this will be X. Move to the right, okay, goes here. The input is E, yes, it is E. Change it to Y. Okay, no problem. Change to Y. Go to the left. So it should look something like this. One more time. The condition for transition is both inputs for this example. If we have multiple tapes, then all of them should be satisfied. To show how flexible is a dual tape Turing machine, look at this example that we saw before. A to the n, b to the n greater than or equal to 1. We solve it this way. And you remember how we had to juggle and go back and forth, find one A and go to the right, find a B to match with the one A. So it was a chaotic thing, right? But now look at how easily we can solve it by a dual tape Turing machine. Here are the requirements. The input is written on the tape 1, and it is okay to use the stay option. Yeah, I put the strategy here for your reference, but let me explain that here. As usual, we start with a happy example. So this is tape number 1, and its content is A, A, A here, and then B, 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 and here we have blank. How about the tape number 2? Tape number 2 doesn't have anything. It has just blank, something like this. So the cursor number 1 is pointing to the first symbol of the string, and cursor number 2 is pointing just one of these blanks. Okay, so what is the strategy here? I try to read all of these A's and write them on the tape number 2, here, here, and here. And then when I reach to the first B, I start matching them with these A's. How can I do that? Yeah, it's very easy. Look at this. I put a loop here, and then I would say on tape number 1, if it is A, don't change it, go to the right. Vertical bar, on tape number 2, if it is blank, change it to A and go to the right. What would happen? In every time frame, Turing machine will check both of these conditions. It asks, it is A? Yes, it is A. Don't change it, go to the right. At the same time, it is blank? Yes, it is blank. Change it to A and go to the right. And this would happen, since it is a loop, this would happen for all of these A's. So it is A, yes. It is blank, yes. At the same time, just change it to A, and this would happen for this A as well. So after this loop, we expect to see something like this. Now what? Now the tape number 1 is pointing to B, but tape number 2 is pointing to a blank. So in one transition, I try to, make some adjustment. So if it is B, it is B. Don't change it, but stay. On tape number 2, it is blank, yes. Don't change it, go to the left. So what is the goal here? I keep this as it is, but I want to move this to point to the A. Because in this case, I can match this B with this A. Okay, I can do that in a loop. So let me create a loop here. I would say if it is B, don't change it, go to the right. At the same time, if it is A, don't change it, go to the left. So what would happen after this loop? All of these B's will be matched with each A here, okay? And at the end of this loop, this cursor is pointing to this blank, and this cursor is pointing to this blank. And then, if really the number of B's and A's are equivalent, then we need to get this. If it is blank, don't change it and go to the right or left or even stay. We don't care about this. And on the tape number 2, it should be again a blank. Don't change it and go to the left, right, whatever. Yeah, we don't care here. The important part is that we made sure that all of the A's and B's are equal. Okay, so this design is based on this example. This is, as I explained, this is a very good practice. During the design, you make this happy example like this. After that, we can take care of the other situation that can happen. For example, if the number of A's is more than number of B's, or number of B's is more than number of A's, or if the string start with the B, what would happen? Then we can take care of all of them and try to break the code. How the formal definition looks like? Yeah, the same septuple, and most of them are equivalent to the standard Turing machine, except the delta that is always different. Instead of having one input symbol, we have several input symbols. And on the range side, the same thing. We have several input symbols, and also we have several movements set. It means that we have the Cartesian product of several movement sets. And for the tape alphabet, gamma to the n is equivalent to Cartesian product between all of them. So with these changes, then we can create the formal definition of the multi-tape Turing machine. Okay, the next question is this class more powerful than the standard Turing machines? No, this theorem is showing that they are equivalent, and we can simulate multiple tape with the standard Turing machine and the other way around. Okay, so for the first one is always a trivial proof because multi-tape Turing machine can simulate a standard Turing machine. Of course they can. We just need to use only one tape and don't touch the second or more tapes at all. So it will be equivalent to a standard Turing machine. But for the other way around, I mean simulating multi-tape with the standard Turing machine, that always is something, a big deal. We need to work on that. And this simulation is possible. We need to put the second tape somewhere here on the standard tape. So for example, we can assign this portion for the, let's say, tape number 2. And whatever we can do on tape number 2, when we have dual tape, we need to simulate it here because we have the ability to move this cursor back and forth. Whatever we want to do with tape number 2, we move it here and we do that and then return back to tape number 1. Yeah, this is doable and we can prove that it is possible, but we are not gonna do that in this course. So this theorem is showing that, yeah, both of them are equivalent. Now let's see what is non-deterministic Turing machine. So just to refresh your mind, what was the definition of the determinism? During any time frame, there is no more than one transition. So we have these kind of machines with this feature. Okay, so how can we violate the determinism? We already know that. We have two ways to violate the determinism: lambda transition and having multifunction. But even though theoretically we can define lambda transition for the Turing machine, but historically they didn't do that. Probably there are some reasons. So we don't have lambda transition for the Turing machine at all. Probably you are asking why. It is a little bit big question mark for you. Yeah. So just remember what was the reason what we use the lambda transition. Mostly we use lambda transition for combining simple machines and also for parallel processing. But the point is, for combining the machines, simple machines, we really don't need lambda transition. We just learned that how easily we can combine simple Turing machines and to create a more complex one, right? So for combining, we really don't need lambda transition. How about the parallel processing? Yeah, just multi-function is enough. Okay, so probably that's the reasons that they didn't define lambda transition for Turing machines. Okay, now let me take some examples for the multifunctions. Yeah, here the input is A, change it to B and go to the left. The input is A, change it to C and go to the right. So as you see, we have two possibilities when the input is A. So definitely this is a violation of determinism and it is a multi-function transition. How about this one? No, the input is A, the input is C. So definitely it's not. How about this one? Yeah, again, the input is A, the input is A, right? Yeah, we don't care that these operations are different, but the thing that we really care is the input symbol. So this is definitely a violation of determinism. What would be the formal definition of non-deterministic Turing machine? We will be using the same septuple, but as we have seen so far, we just need to put a power set on the range side. And if we do that, then the function will be total function. Since these things are very similar to whatever we've seen before, so we don't really need to go over that. So here is a simple example. The example is asking you to draw the transition graph for this subrule. So it's very easy. So it means that if it is A, change it to B, go to the right and go to Q1. And the next one is saying that if it is A, change it to C and go to the left and transit to Q2. Another question is how non-deterministic Turing machines behave if they have multiple choices. Yeah, we have a standard and very general rule for all of these. When machine has multiple choices, it starts parallel processing. Okay, and all of them looks like exactly the same. So whatever we said for the NFAs and NPDAs is applicable for Turing machines as well. And I put these instructions for your reference. It replicates itself and whatever. Yeah, blah, blah, and it initializes the new processes with the current configuration and so forth. So the only thing that we need to know is what is the configuration, what information we need to have a configuration of the Turing machine. The configurations, it has just current state of the transition graph and the tape and its content and the position of the cursor. These two pieces of the information will be the configuration of the Turing machine. In this section, we want to find out which one is more powerful. I mean, non-deterministic Turing machines versus standard Turing machines. But we have a theorem that is saying both of them are equivalent. Okay, so how can we prove this theorem? Again, we have two things to prove. Non-deterministic Turing machines can simulate standard Turing machines and vice versa. Okay, how can we prove the first one? It means that we have a language and we have a standard Turing machine for that language. Now the question is, can I construct a non-deterministic Turing machine for the same language? Can I do always this? Yeah, exactly. This is the question that we ask for the DFAs and NFAs. You remember how we converted the definition of DFAs to NFA? Yeah, we can do exactly the same thing here. The conversion procedure is exactly the same as DFAs to NFAs. Because if you remember, what is the difference between the standard Turing machine and non-deterministic Turing machine? The only thing is on the range for non-deterministic, we have a set. And how can we convert the range of a standard Turing machine to this guy? We just need to put curly braces around them. So easily we can convert the mathematical definition or formal definitions of standard Turing machines to non-deterministic Turing machines. How about the other way around? I mean, how can we prove that a standard Turing machine can simulate non-deterministic Turing machine? Yeah. So the mathematical proof definitely is very hard and beyond of the scope of this course, but we can intuitively prove that, or let's say imagine how the proof can look like. Okay, let's do that. It's a good experience for us. Before that, let me remind you the one-dimensional projection again. So what was one-dimensional projection? If we have a walk like this, A, and this is the walk, right? A, and B. So we can unwind this chain or a strain, whatever we can call this, something like this. So Q1, then this is A, A, and B. So we can unwind this walk and project it on one dimension. This is easier to understand a process. Let's see how. Imagine this is a Turing machine. How come it has only one symbol here? For simplicity, let's assume that we have A, don't change it, go to the right. If it is B, don't change it, go to the right. So I just removed this part and I kept this for simplicity and readability purpose. Okay, so this is a Turing machine, and the question is, if we feed AB to this machine, how many processes will be created? Yeah, let's organize all of these processes on a tree that we call it process tree. So this is the tape. Let's say this is a common tape between all of the processes, but you know that every process has its own independent tapes. But for this simple example, we can show the same tape for all of them. All right, let's start from here. Read A, and we are on Q0 as the starting configuration. If read A, then how many processes will be created? Because Q0A, it can stay here, it can go here, and it can go here. So we will have three processes. All right, let's see. Q0, go to Q1, or go to Q2. For all of them, the A is consumed and the cursor will move to the right. How about the B? We need to calculate for every process separately. We are here, Q1B. The Q1B, one possibility is to stay on Q1, one possibility is go to the Q3. Okay, how about Q2? For Q2 and B, we have only one possibility, go to Q4. How about Q0 and B? There is no B, outgoing B. So this process will be killed because it doesn't have any transition for B. So it will die. Okay, we can continue for all of the other symbols as well. All right. So right now we have one process here, two and three process active. All right. So again, we start from the Q1. Q1A. Q1A. There is no A here. So we anticipate that this process will die. How about Q3A? Q3A, it has only one possibility to stay at Q3. How about Q4A? We have one possibility to stay and one possibility to go to Q1. Okay, so this A will be consumed. Now we need to calculate the B for everyone. So Q3B doesn't have any outgoing for B. It has to die. And how about Q1B? One possibility is go to Q1, one possibility is go to Q3. And how about Q4 and B? There is no possibility for Q4, so it will die as well. And we are out of symbols here, and one process is in Q3 and one process is in Q1. So actually at this point we don't care about whether it is accepted or rejected, but if we wanted to consider that, yeah, one process will accept that because it can halt in an accepting state. But we have other points here. So when you look at these processes, what do you see in the processes? Can we consider every process as a standard Turing machine? Of course, yes. So every process that starts from the initial state until it halts somewhere, for example, here, this guy. So these are the leaves of this tree, right? When you look at these processes separately, you see one standard Turing machine, right? So can I conclude that a non-deterministic Turing machine is in fact a collection of standard Turing machines? Yes, of course. If this is the case, it means that if I can have a bookkeeping for the processes, can I simulate a non-deterministic Turing machine with a standard Turing machine? Of course I can. It's hard, but I can do that. So I have one unlimited, let's say unbounded tape, and I have one input string here for a standard Turing machine, and I can use the rest of this tape for simulating anything. Let's say I keep track of the one process here, and so forth, right? So it means that a standard Turing machine can simulate non-deterministic Turing machine. All right, so you agree that non-determinism didn't add any power. It just speed up the computation. And speed is not a deal for us. We don't mind about the speed. So speed will be a matter of concern when we are talking about the complexity theory. But right now that we are focusing on the computability, speed is not a matter of concern for us. That was a very good conclusion here that non-determinism does not add any power. And another point I want to point out here is that quantum computing, it tries to implement non-determinism. So based on this knowledge we got so far, it means that even quantum computing does not add any power to computing. Okay, so it just speed up the process of computation. Okay, so I'm gonna stop here and see you guys in the next video.